Hello and welcome to this video on rectilinear motion. Usually I would start with a really gumpy statement telling you that linear motion is everywhere, but honestly, it isn't. Things in real life move more often in unrectilinear ways, like curves and waves and spirals in 3D space. But to study those, it's essential to understand how things move in the most basic ways, as a straight line. This is rectilinear motion. Linear motion is a type of kinematics, which is a study of how things move. Kinematics are important because it is able to describe the motion of objects in quantified ways, and we as engineers really like this sort of thing. It allows us to pinpoint exactly how something moves very precisely. And this means we can predict all sorts of things, like what sort of path a thing would take, so we can plan for it, sort of like looking into the future. And this is great because as engineers we're basically employed to make things that don't kill people. So the most basic form of kinematics is rectilinear motion, which describes the movement of an object in one dimension or along a straight line. Firstly, we have to assume a couple of things. We'll simplify an object down to a point mass where its size can be ignored. This can usually represent the object's center of mass because the forces which act on it to make it move can be simplified to act on the center of mass. We also assume there's no air resistance, but that's another story called kinetics. In kinematics, we can take a look at the position, velocity, or the acceleration over of an object. To describe them, we should describe it with respect to a certain point, usually over a period of time, and this point is stationary, we call the origin. From this origin, we can measure out things we want to examine, like position, velocity, or acceleration. Now, position is a measure of distance away from the origin we defined earlier on, and velocity is a measure of the rate of change of the position. Similarly, in acceleration, that's a measure of the rate of change of velocity, or in terms of differentials, it's a second derivative of position over time. Excellent. So let's take a look at three different scenarios. Let's take Professor Prusty here, and he's doing the most basic thing. He's standing still, not moving anywhere. So compared to the origin, he is always 2 meters to the left of it. So the graph, it's going to look like this. You have your position on the y-axis, the time on the x-axis, and the position constant over time at 2 meters. Awesome. Let's say Professor Prusty sees a delicious donut 20 meters away and he walks towards it at a constant velocity of 2 meters per second. Your graphs are going to look like this. We have our position graph and a velocity graph, both over time. Now the velocity is constant at 2 meters per second, and because v is a gradient function of position, our displacement graph is going to have a slope of 2 everywhere. So naturally our graph is going to be a straight line that looks like so. Nice! After eating the donut, the pink food coloring has made him rather excitable, so he takes a really enthusiastic run. He increases his running speed at 1 meter per second each second, so after 10 seconds he's clocking world record speeds. But who knows, Professor Prusty might be some sort of Superman. The graphs are going to look like this. We have a displacement and velocity graphs as usual, but also an acceleration graph this time. Similar to the last time, the acceleration is constant at 1, so our velocity is a straight slope with a gradient of 1. But this time, the displacement gets larger and larger as we go on, so we can see the distance from the origin increases parabolically. Awesome, now we've covered the easy stuff, it's time to take a look at the maths. Let's take position as s. The rate of change of position is the velocity, and we can express velocity as ds dt. The rate of change of velocity is the acceleration, So we can express this as dv dt, or the second derivative of displacement on time. With these simple definitions, we can do some pretty trippy stuff with it. So what if we want to get rid of the term for time? It's simple. We have v equals to ds dt, and a equals to dv dt. So isolating the dt, we can get dt equals to ds on v, and dt also equals to dv on a. Equating them, we can get ds on v equals to dv on a. And thus, when we cross multiply them, we have ads equals to v dv. So when we divide each side by ds or dv from this line onwards, we can get change of velocity with respect to displacement or vice versa. Why we might want to get rid of this term for time is that there are some applications where acceleration changes with respect to the distance away from the origin at which it's placed, like magnetic forces, things in simple harmonic motions, and objects in gravitational fields. So the above formula comes in pretty handy for this sort of thing. There are more extended applications of rectilinear motion outside of this video, but that's the next story for next time, and that's curvilinear motion. Thanks for watching, and I have hoped you enjoyed this video.